Okay, I'm here to talk to you about parallel circuits now. And we have, just like we had with series circuits, a series of equations that describe parallel circuits. And some of these make sense, but some of them you have to really think through. They're not necessarily as intuitive as the series circuits things, and they actually might go against our intuition. So the first one just talks about total current, and when we talked about conservation of current, this should make a lot of sense to you. The total current is equal to the current through like resistor 1, which is plus resistor 2 plus resistor 3, or component 1 plus component 2 plus component 3. Because the components don't have to be resistors, they could be anything along these paths. So I have a circuit here that has R1 and R2. You can imagine if I put an R3 in here, you could measure the current through those. And each of these, maybe there's 1 amp through that. Well, maybe there's 2 amps through this. Maybe there is 1 amp through that. It's got twice as much resistance, so it should have half as much current. If you look at this, because current is I is V over R. And the resistance of this one, whatever it is, let's say it was also 20 ohms, would also be 1 amp. So your total current would be 4 amps, right? You've got 4 amps in, 4 amps out. The total resistance, the total current for the circuit is 4 amps. That one is pretty straightforward. Now let's get to a slightly more complicated one, if I can figure out where I put my eraser. Okay. V equals V1 equals V2 equals V3. It's basically a fancy way of saying that the voltage in each of these different paths is the same. So if R1, R2, and R3 have different resistances, but that doesn't matter because the voltage drop for all 3 components should be the same. It should be 9 volts. 9V, 9V, 9 volts. So 20 ohms, 10 ohms, they all have a 9 volt drop. And just think of it this way. Electricity gets to this part of the path and it wants to split up, but it has to start at a certain voltage and end at a certain voltage. Basically, it needs to lose like 9 volts from between when it starts and stops. So regardless of which path it takes, it still needs to have a 9 volt difference. Just like if you had water flowing over a waterfall. So water flows over a waterfall and hits the bottom here and stream goes that way. Well, maybe some of the water goes this way and has a separate smaller waterfall and boom, 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 and has another waterfall there too. If this is comparing it to circuits, maybe this would lose 9 volts and this one would have 2 waterfalls, but those 2 waterfalls would lose a total of 9 volts also. So you've got to have the same total change. In circuit terms, this would be like a circuit that looked a little bit like this. You have path 1 that has 1 resistor, and path 2 would have 2 resistors, and each of those resistors would lose a little bit of voltage, but the total is going to be 9 volts, because regardless of which path you take, you're going to lose 9 volts. So when this says V1 equals V2 equals V3, it's really talking about each path. Think these are like each path. So path 1, path 2, path 3, they all lose 9 volts. That's equal to the total voltage of the battery. This is getting into a hybrid circuit we're going to talk about in a different video. The thing where it gets most unintuitive is where you get to resistance. And this is the resistance equation. R equivalent is equal to 1 over R1 plus 1 over R2 plus 1 over R3. And if you think about it, what this is telling you actually is that R equivalent changes as you add resistors and actually gets lower. So let's start with this one, R1 and R2. You've got 10 ohms and 20 ohms. So the equivalent resistance of that, I made a mistake by the way. Let me correct this mistake. That should be 1 over R equivalent. Oopsie, okay. 1 over R equivalent is equal to 1 over R1 plus 1 over R2. So 1 over 10 ohms plus 1 over 20 ohms gets me a total of, let's see, 1/10 and 1/20 is the same as 2/20 and 1/20, or 3/20. So that is equal to 1 over the equivalent resistance, which means your equivalent resistance is equal to 20 over 3. We throw the ohms in here, and you'll see that the ohms come out in the right way. 20 over 3, which is equal to 6.67 ohms. So number one, the total resistance is less than either of these two resistors. It's lower than the lowest one. It's lower than 10, and it's definitely lower than 20. Now let's add another resistor and see what happens. So let's add an R3 and say that's another 20 ohm resistor, and recompute this. I'm going to erase some of this, but not all of this, because we're adding just another 1/20 here. So it's 2/20 plus 1/20 plus 1/20. The ohms on the bottom. So you get 1 over equivalent resistance is equal to now 4/20. So our equivalent is the inverse of this. It's 20 ohms over 4, which is 5 ohms. So adding an extra resistor actually decreased the overall resistance of the circuit. And this is where it gets kind of anti-intuitive, because when you are in parallel, I'm going to erase this in a second, so pause if you want to write anything down. But when you are in parallel, adding resistors in parallel will decrease the overall resistance of the circuit. And one way to think about it is, imagine you go shopping and you have two cashiers, one of whom is going really slowly. Cashier 1 is going really slowly. And we're going to call cashier 1 a resistor, right? Who's a big resistance. Cashier 2 is going pretty quickly, so that would be like a small resistance. And maybe a third cashier comes along to give us another option. And that third cashier might be going very slowly also, and thus have a big resistance. But it's still going to ease the burden on the first two, and it's going to make it easier, even if the person's slow, it's going to make it easier to get more people through and checked out and paid for their groceries, because you have an extra path to take. So adding paths decreases the resistance, even if some of those paths have a lot of resistance to them. If we look back at the problem that we had here, we've got a 9-volt battery, 3 resistors, and we know the total resistance of the 3 is 5 ohms. We can figure out what the total current is through this, and also look and see what the current is through each of these paths, 1, 2, and 3. So I'm going to do that right now. And again, we're going to use Ohm's law, V equals IR, aka R equals V over I, or however you want to put it. So let's think of this. The total resistance is 5 ohms, 9-volt battery. So if you want to look using this at the current, I equals V over R. And current total then, let's just look at the total, is going to be V total, which is 9 volts, over equivalent resistance, which is 5 ohms. So that should equal 1.14, right? 1.8 amps. So I total is 1.8 amps. Now we can also apply the same logic to each of the resistors. So let's instead look at the current through resistor 1. I1 is equal to V1 over R1. And V1 is 9 volts, and R1 is 10 ohms. So that should be 9/10 is 0.9 amps. So that is 0.9 amps. We do the same with resistor 2, I2, V2, R2. V2 is now 9 volts also, but R2 is 20 ohms. So 9 divided by 20 is 0.45 amps. 0.45 amps. And if you did the same, R3 is the same as R2, right? So that should also equal 0.45 amps. And according to this, the total current should equal I1 plus I2 plus I3. So you could say, hey, I know that I1 is 0.9 amps, I2 is 0.45 amps, I3 is 0.45 amps. You add them together, you get 1.8 amps. 1.8 amps is the same as we got here with Ohm's law using the equivalent resistance, the 9-volt resistor. So everything is worked out. It's confirmation that we did this math correctly. Again, you can do variations on this. It takes a little bit of practice, but once you get through it, it's just kind of, it comes a little more naturally. It's like problem solving. It's almost like solving a Sudoku puzzle, I think, where you just have to logic through it and you can figure out what's going on. Next, we'll take a brief look at hybrid circuits to see how that works. But for now, thank you very much for watching.